Hello everyone, Stéphane Couture here from Evident, working with the Global Product Support team, and welcome to this edition of What's New in MXU. Today I'm joined by Trevor Tartaglia from the Omniscan Product Management team. Trevor is fairly new to the team. Welcome aboard.
Thanks, Stéphane. Thanks for having me.
Today we'll be talking about MXU 5.10 for the Omniscan X3 and Omni PC. As you can see on the table, we have a good amount of demo material. So first of all, what are we going to talk about, Trevor?
The first thing we're going to talk about today is the new phase coherence imaging, or PCI, that's going to be exclusive to the Omniscan X3 64. PCI is going to be a variation on TFM, and rather than using the amplitude, we're going to use the phase information of our A scans to generate our image. The big advantage that we're going to have with the Omniscan X3 64 is that this image is going to be a live image in real time while we're going to be scanning. The phase coherence imaging is also going to be a lot more sensitive to small defects and less sensitive to large defects such as the back wall, creating a better signal-to-noise ratio in scanning a lot of materials, especially noisy or attenuative materials such as austenitic steel or stainless steel. It's also going to make sizing a lot easier because we're going to have some tip diffractions from cracks and whatnot that are going to be a lot easier to see. In amplitude TFM, we're going to see them, but they're going to be hard to distinguish from our background noise, versus in PCI, it is going to be really obvious and really easy to see while we're doing our scan. So to show this, switching over to the X364, here I have a block with different height notches at 20, 40, 60, and 80% of my depth. Starting in conventional TFM, if I move over to my 40% notch, we can see the tip of my notch, but it's hard to see the vertical component, which is pretty characteristic of TFM. And my corner trap is going to be difficult to distinguish from, is it the actual corner trap or is it actually a defect that's going to be at that diagonal plane. And if I switch over to my 60% notch, it's going to be the same thing, but even more exaggerated. And if I try to make my corner tip, my tip diffraction a bit more obvious and I increase the gain, my background noise is going to be even harder to distinguish from my actual defects, making the choice and the analysis even harder to do. But if I switch over to phase coherence imaging, I only have to use one menu in order to do this, and a slight wait depending on the size of my setup. After about 8 or 9 seconds, I'm going to be in phase coherence imaging. First thing you're going to notice that the gain control is grayed out. That's because the gain has absolutely no implication while using phase coherence imaging. It's going to be based purely off of the phase of my defect. And we can see with the PCI, both of the corners of my notch are going to be really obvious. The actual corner trap is going to be just one concentrated point. It's not going to have that ghost echo from the side. And we can even see some of the vertical component of my notch. If I switch it back over to my 40% depth, we can see that the coherence level of my notch is identical or very similar to my 60%. Another advantage we have with PCI is that the amplitude of the signal is going to have no incidence on the actual coherence level. So wherever we are in our TFM zone, as long as sound is getting to that point, we're going to have a good coherence level. When sizing with phase coherence imaging, it's going to be even easier. All I have to do is find the hot spot at the top of my defect, set my cursor on that position, and that's going to be the position of my defect. So I know that the depth of my defect is at 15 millimeters. I have a 10 millimeter notch in a 1-inch block, so the sizing is correct. It's easy to say all this with a perfect defect with a notch. So we're going to switch over to Stéphane. He's going to show us the same kind of information, but with natural defects.
Right. So we're just going to load the setup file for this one, the demo. As you can see on the part, I have a dual linear array probe. So that's also one new feature of the 5.10 software version. We now support TFM with the dual linear array, dual matrix array probes that we offer for both angle beam and 0 degree. Moving on this part, we have a sample that has some H2S blisters with connecting stepwise cracking, and we're already pre-set up. If I move around on the part here, we can see the TFM signal. That looks decent or to an extent great. But if you look closely, the link between the back wall and those blisters, it's not 100% confirmed. So we're losing some of those linking when we're getting near the back wall. So as Trevor explained, this is based on the amplitude of the signal, and without going into the scan plan menu, we can rapidly switch over from amplitude to phase coherence. We get a switch of color palette as well, just to represent that we're in a different mode. And now as I move, we have a much cleaner resolution. Those link between the blisters, the cracking, and the ID are more apparent. They're better resolved. And you can also see that the signal is far less noisy compared to TFM. So that's one application so far where this method shines. We can also thank creep damage. We can also thank HTHA. Both will have a similar Flaw signature, and we'll have great results there.
There's going to be a lot more material that's going to be put out about the phase coherence imaging. We're going to have a white paper explaining in depth how it works, as well as a few blog posts and a getting started guide to help you get started with the PCI on the Omniscan X3 64.
Great, thanks. So that's one feature that's going to be our, let's say, flagship feature for this release. Of course, we're not a one-trick pony, so so next feature available with the 5.10 release is going to be the Tcg calibration, now available for TFM. This has been highly requested, highly anticipated too. We listen. It's now on board the instrument too. So just making sure we're connected. And as I move around, I'm just moving my A32 probe on the good old nab ship block, hitting two separate side drill holes. So just to perform the calibration real quick to show you how it is implemented, how it's included. You go in the drop-down menu, burger menu, select calibration tools. And just like in phase array where you select your calibrations, you first select your group or wave set, hit Tcg, and then it's basically the same environment. So you basically start by boxing your reflector vertically. With Tcg or with TFM, pardon me, we can also box horizontally. So if you ever run out of sensitivity or the amplitude drops down too much and it's out of your zone of interest, you can cut that out. I'll just leave it full for now. And bear with me, I'm going to do this fairly quickly. So you move from left, clear envelope, to right. We record an envelope just like we do in phase array. Try to be as smooth, consistent as possible at the point. And as I move over to validate my calibration, I should have something fairly consistent at my target amplitude. So that's one point, and just like any regular TCG, we can duplicate or repeat for point number 2, 3, 4, as per your procedure requires. Accept TCG, done. And the correction is now applied to the live signal. As you can see, orange, max amplitude 87%. Close enough for a quick live demo scenario. So that's available with 510, works with our angle beam probes, our 0 degree probes as well. That's one more feature in the box. going to switch over to Trevor then for one more trick that we have.
Thanks, Stefan. The final feature we're going to talk about today is going to be the new weld overlays for phase array with COD. Previously, we had the zone of interest in TFM, which was curved around the shape of our part. And phase array, we have the different legs, which are also curved in order to demonstrate the thickness of the part for each leg. But now we're going to have the actual weld overlay, which is going to be repeated in each leg and also is going to adapt in order to meet the sound path in that same part.
Correct.
So here in this part I'm going to have a double V weld, and we're going to see in the S-scan, each leg of the weld is going to be slightly different in order to compensate for the sound path in the part.
Right. And just to provide some more info, so when we refer to COD, AOD, we mean that the weld is axial to the pipe, and the wedge is curved to conform to the circumference of the pipe to be inspected. So the challenge is that since we're not on a flat surface anymore, reflections towards the ID and OD will change the angle of reflection, and then it's going to be harder to actually predict where the beam is going.
Moving to the Omniscan X3 screen, we can see that we have the legs that are shown in our S-scan. But as well as the legs, we also have the weld overlay. Very similar to what we had with a plate before, but each leg is going to adapt the weld overlay so it fits with the sound path of the part. Because as we move deeper into the reflections, the part is not always going to meet the weld at the exact same angle. This is going to make identifying defects a lot easier. If I move on my part here a bit further, we can see that there's a has crack on the near side of my weld, and by using the weld overlay, it's a lot easier to identify the type of defect because we can see where it is situated within my weld.
Great, good demo. Thanks, Trevor. So that concludes the What's New 5.10 edition for today. Thank you for joining us. If you have questions, if you'd like to know more about anything that was presented today, feel free to reach out to us or your local sales representative. Also, as mentioned, we'll have more documentation on the website through blog posts, white papers, and stuff to really get you up to speed on the new software update. Thanks again for joining me today, Trevor. Pleasure. And see you next time.
Thanks, everyone.